In this video, we are going to be talking about what light is and just a few things that light can do so that we can understand light and what we see around us. And this will help us as we go on and learn more about astronomy, because for astronomy, you need to be able to understand light to be able to see how is it can we study things so far away. So the first thing we need to know about light is a wave. So it goes along with what we have been studying it to this point. And you know, light, we can see like its effects. We know when the lights are on, when the lights are off, but there are a lot of things that light can do that maybe you haven't noticed or you haven't had a chance to see that will be seen in this class. So the way we know that light is a wave is that light can do things that waves can do. So one of the things that light can do is it can reflect off of objects, okay? So just like these water waves are reflecting off a surface, so you can see the water waves are coming in from this direction, hitting a surface, and then going off in this direction. Now, in some ways, you're like, well, that's not all that special. That doesn't really prove that light's a wave, because I can throw a ball at a wall and it bounces off, and isn't that a reflection? And you're kind of right there, that in some ways that's not enough to show that light is a wave. But there's an example there of a laser reflecting. Okay, so again, showing that light can reflect off of surfaces. Another thing that light can do, that waves can do, is it can refract. And so we can see as the waves here are moving in this way, when they encounter a boundary, they're being bent and going off in a different direction. And so this behavior is called refraction. And so what happens in refraction is when the light waves are going in from, this is going from a slow material to a fast. Okay, so when the waves go from in that boundary from a slow material to a fast material, they bend, and it would do the opposite if it was traveling the other way from a fast material into a slow material. Okay, so again, we can see that light does this too. We can see the laser as it's going from air, which is a fast material, to the plastic or glass, whatever that is. It's bending, it's refracting as it goes into the slow material. And that's something that, you know, if you just think of light as just a particle like a tennis ball or something, if I throw a tennis ball into water, it certainly slows down, but the direction it's headed does not change. So that's something where you need a wave to really demonstrate refraction. Another thing that a wave can do that a particle, or like I can't think of a tennis ball, is doing is diffracting. Okay, and so here's a picture of water waves diffracting. You can see the water waves are going into, let me choose a different color so it's easier to see on the pen. Okay, so the water waves are starting out flat, and then they're going through these little small holes in this barrier here, and they are becoming curved as they go through it. Okay, and so this is something again that light can do, and it's hard to see, you know, the curving of the light. You can see the effect of it, the pattern that gets created, and we'll talk more in the demonstrations tomorrow about like where the diffraction comes in. Since light is waves, it can interfere with itself. So this picture kind of represents, well, this is probably like with water waves doing it, but we saw with sound waves when we wandered back and forth around the classroom that there was dead spots where there wasn't much sound, and there was louder spots. Okay, and so the sound waves can interfere to get louder and quieter. Well, light waves can interfere with each other, and so you can get, again, patterns of brighter and darker. Okay, which is essentially what happens in this example of diffraction also. Okay, so because light can do all these things, just like waves can do all these things, we represent light as a wave. Okay, and so what light is it's a wave. It's actually, light is not a mechanical wave like the waves we've been learning up to this point. Light is an electromagnetic wave. And just like all waves, light needs something to be vibrating to cause that wave. And so what vibrates in light is charged particles. So electromagnetic waves come from vibrating charges. And what that does is it changes the electric field, which then changes the magnetic field around it. And so that vibrating, that oscillating electric and magnetic field then propagate through space. Electromagnetic waves need no matter to travel. And the other thing we know about electromagnetic waves can move at the fastest speed possible in the universe, and that is the speed of light. Okay? So the speed of all electromagnetic waves in a vacuum is known as the speed of light. And in physics, we just call it c. So like in the E equals mc squared, that c is the speed of light. Okay? And so all electromagnetic waves travel at that speed when they're in the vacuum and they're not going through material, but they do go slower as they go through other materials. So light travels slower through glass than it does through air, and slower through water than it does through air, and so on. Otherwise, you couldn't have refraction. We know that light behaves as a transverse wave because we can polarize it, and polarization just means that, so light normally coming off of sources is not polarized, which means that the waves are arranged in all sorts of directions, but we can pass those through polarizing filters, which then make it so only one direction can get through. So if we look at this picket fence analogy is oftentimes used, where the wave, if I have two picket fences that are lined up in the same direction, the wave can get through. But if I line up perpendicular fences perpendicular to each other, the wave can get through the first one because it's lined up with it, but it can't get through the second one. So light becomes polarized through a couple different ways. One way that light can become polarized is by reflecting. So reflection polarizes light parallel to the surface. Okay, so we can see in this image here, when the light hits the lake polarizes all the light horizontal that reflects off it. So if you wear polarized sunglasses that are oriented to cancel out that horizontal polarization by having vertical slits, then it can't get through. So now we don't have all the glare coming off the lake. So that's the advantage of having polarized sunglasses. So light is a wave, and really what we consider visible light is just one small part of a huge spectrum that goes all the way from radio waves to gamma rays. Okay, so on one end of the spectrum, the radio waves are very low in energy and come from things that have very low temperatures. Okay, so this is the low energy side, all the way up to gamma rays, which are the high energy side of light. Okay? If we notice that we're given like the wavelengths on the radio side, the wavelengths are very long, and on the other side then they are very short. Okay? The frequencies on this end, this is the high frequency side, and over here, whoops, sorry, wrong way. This is the low frequency side, and over here is the high frequency side. Okay? So these pictures in here just kind of give you a scale of what sizes. So the wavelength of infrared light is about the size of a needle point. The wavelength of visible light is about the size of like bacteria, okay, and so on. One thing about light is you can only image things with light if it's near the size of what you're looking at. So you can't image on the point of a needle with a radio wave, it's too big. We can't image molecules with visible light, it's too big. Okay, we have to use other types of light to see those. So the way we see light in human experience, we have rods in our eyes which are basically they're either on or off if they get hit by any kind of visible light at all. So they are only like, let us see black and white, but they're more sensitive. And then we have cones, which you have three types, the red, the green, and the blue. And this graph here shows that the red cone is most sensitive to a wavelength of light around 600 nanometers is going to be where it picks up things the best. And a green cone is going to be most sensitive to light that's around 550 nanometers. And then a blue cone is going to be most sensitive to something around 475 nanometers. Okay, so that's the reason we have 3 cones. That's why it takes only 3 colors to make up other things. Okay, and you can see there is some overlap there. And so basically our brain interprets, hey, if the blue cone's excited and the green cone's excited this much, then it's this color. And if the green cone and the red cone are excited this much, it's going to be this color. If it's something in the middle, you know, then it's this color. So by which cones get excited is how our brain interprets what color something is. Okay? When we're dealing with color addition, as we've seen in the demonstrations, is that we can think of color addition with light. When we're putting colors together, we do it additively, so light colors add together. And when we use pigments, okay, then they subtract colors. So a yellow pigment subtracts blue out of the incoming light. A cyan pigment subtracts out red. Okay? So that subtracts out the red. A magenta pigment is one that subtracts out green. If you look at a green pigment is one that subtracts out red, red and blue. So it's minus red, minus blue. A red pigment is minus blue, minus green. And then a blue pigment is minus green, minus red. Okay? So and then of course a black pigment is one that subtracts everything. So one of the things I want you to be able to do to show me that you understand how color works is to be able to predict, like, what color should something look when it's shown under different colors of light. Okay? So if I have a white piece of paper under a white light, my eye is going to say, okay, white light comes in, it's made up of, I can pretend it's made out of just red, green, and blue light. That comes in, bounces off the white piece of paper. White doesn't have any pigment, so red, green, and blue all bounce off. My eye sees red, green, and blue and say, okay, that paper is white. Well, what if I change the color of the light? So instead of having the light be white, what if I use a red light? Okay, if I have a red light, that means that only red light's coming in. If only red light's coming into my white piece of paper, only red light can bounce off. And so my eye sees only red. So even though that piece of paper is white, I can only see it as red. Okay, what if instead of a white light, or let's go back, we can keep a red light here. Okay, but let's say it's a blue piece of paper, which means it has a blue pigment to it. Okay, so now still I only have red light coming in, but if we go back and we look at, well, a blue pigment here is a pigment that subtracts green and subtracts red. Okay, so if I'm sending red in, but blue subtracts red, then I can't have anything coming off, and so my eye sees black. All right? What if, again, we'll just stick with the example of a red light. Paint my light red again. Oops. Okay, never mind. Blue light. We'll go with blue light. I don't know why it was blue. Okay, so we're only sending blue light in, and let's say right now we'll use a cyan piece of paper. Okay, so cyan is white minus red, and so it subtracts red light out, but there was no red light coming in the first place, so it doesn't matter. But blue can be reflected off cyan, so that would look blue to me. So even though it's a cyan piece of paper, it would look blue. So this is one of the things you'll be doing in your worksheet, is like saying what color should be coming off. And this is the logic you have to think of. what colors are coming in, what colors are allowed to bounce off. So whenever you're doing this, you need to ask yourself, come on. Okay, and what you see is what you bounce off. Okay, so you can only see the color of something if that's what actually bounces off.